Look around any room. Every swinging door, pitched roof, and intersecting wall relies on precise geometric relationships to function. Angles are the physical realities that govern how our spaces are designed, built, and interacted with every day. We can even see these measurements mapped directly onto human anatomy. If you extend your fingers and look at your open palm, the distance between your thumb and pinky creates a 90-degree angle, with your other fingers marking approximately 30, 45, and 60 degrees. Now, imagine movement. When you push open a hinged door, its path traces a measurable arc. By projecting these degree paths onto the floor, you can physically see how the angle expands as the door swings wider. To communicate these measurements, we use a specific set of classifications. Angles less than 90 degrees are acute. At exactly 90 degrees, we hit a right angle. Expand further, and we get an obtuse angle. The key threshold is 180 degrees, which forms a perfectly straight line, known as a straight angle. Anything strictly exceeding that 180-degree mark becomes a reflex angle. Categorizing these base geometries is the first mandatory step in structural design. Only once we define these base states can we begin to measure, manipulate, and build out complex architectural systems. This is a standard protractor, our primary tool for physical measurement. To construct a specific angle, say 120 degrees, you must first align the protractor's origin point perfectly with the vertex of your baseline. Because protractors have a dual numerical scale, you follow the track starting from 0 on your baseline side, tracing up to the 120-degree mark. Once an angle is established, you often need to divide it into two perfectly equal parts. This geometric process is called bisection, and it is an essential technique for creating symmetrical structural designs. To bisect an angle with a compass, place the point on the vertex and draw a single reference arc that cuts across both rays. This creates two new anchor points on the angle, labeled here as C and D. From those two new points, you draw two intersecting arcs in the space between the rays. The critical mechanical rule here is that the compass width must remain physically locked. Changing the width between drawing from point C and point D will ruin the symmetry. Where those two new arcs intersect gives you point E. By drawing the straight line from the original vertex directly through that newly plotted coordinate at point E, you guarantee a mathematically perfect bisection of your original angle. Adhering strictly to these rules allows builders to translate theoretical angle values into exact, repeatable blueprints. Let's look at how angles interact in pairs. Complementary angles are any two angles whose measures add up to exactly 90 degrees. Supplementary angles are two angles that sum to exactly 180 degrees. A common misconception is that these pairs must share a vertex. They do not. Complementary and supplementary angles are defined purely by their combined algebraic sum. Two completely separate angles, like one measuring 52 degrees and another measuring 38 degrees, are still complementary because they combine to form a 90-degree right angle. These relationships scale up when dealing with structural lines. Parallel lines never intersect, maintaining constant distance. Perpendicular lines intersect at a precise 90-degree right angle. When a third line, called a transversal, cuts across two or more lines, it generates a whole new network of angle pairs. When that transversal cuts across parallel lines, it creates distinct algebraic relationships. Angles in matching positions, like corresponding angles or alternate interior angles, are exactly equal to each other in measure. Conversely, consecutive interior angles, those inside the parallel lines on the same side of the transversal, are supplementary, meaning they add up to 180 degrees. Look at these two marked angles on opposite sides of the transversal line. One measures 60 degrees, and the other measures 8x minus 4 degrees. Based on their alternate interior positions, pause the video and see if you can determine their relationship and solve for the value of x. Because these are alternate interior angles along parallel lines, we know their measures must be equal. We set up the equation 8x minus 4 equals 60. By adding 4 to both sides, we get 8x equals 64. Dividing by 8 gives us our final answer, x equals 8. Identifying these geometric relationships is a literal requirement for urban planning and architectural stability. The structural integrity of power lines, railway tracks, and building grids all depend on transversals cutting accurately across parallel systems. Here is a final summary for your notes. The left side catalogs your core angle types and construction tools, while the right provides your transversal legend. Remember, alternate and corresponding pairs are always equal, while consecutive interior pairs sum to 180. Geometry provides the invisible, logical framework that ensures the physical world remains standing, perfectly aligned and securely built.